Inverses of matrices, lesson 5-5. The big idea, most 2 by 2 and most 3 by 3 matrices A have an inverse A to the negative 1 power, which stands for A inverse, of the same dimension. So if you have a 2 by 2 matrix, its inverse is also going to be a 2 by 2. This satisfies that when you take the inverse matrix times the original matrix, you get out the identity matrix. Okay. What are inverse matrices? The idea of an inverse of an operation runs throughout mathematics. Recall that two real numbers, A and B, are additive inverses, or opposites, if and only if A plus B equals 0. So for example, 7.3 and a negative 7.3 are additive inverses. The sum of two additive inverses is 0, which is the additive identity. Two real numbers A and B are multiplicative inverses or reciprocals if and only if A times B equals 1. So for example, pi and 1 over pi are multiplicative inverses. The product of two multiplicative inverses is 1, and that's what happens in matrices. Okay? If you take the inverse matrix times the original matrix, you are going to get out the identity matrix, which is similar to regular math where it equals 1. Okay? The definition of inverse matrices under multiplication follows the same idea as the inverses mentioned above. 2 by 2 matrices A and B are inverse matrices if and only if their product is a 2 by 2 identity matrix. So you know two matrices are inverses of each other if you multiply them together and you get the identity matrix. Because matrix multiplication is not commutative, the definition of inverse matrices requires that the product in both orders of multiplication be the identity. To be multiplied in both directions, the matrices must be square matrices. Okay, that's a key point. Must be square matrices. Those with the same number of rows and columns. So, an inverse can be a 3 by 3 matrix, a 4 by 4 matrix, but you can never have a 2 by 3 matrix have an inverse. Cannot happen. Furthermore, as you will see, not all square matrices are invertible. Not all of them have inverses. So we got to check this out. Notation for inverse matrices. The real number x to the negative 1 power is equal to 1 over x, the multiplicative inverse of x. So for all x that can equal 0, similarly, the symbol m to the negative 1 power, matrix m inverse, stands for the inverse of the square matrix M if M has an inverse. Many graphing calculators and all CAS calculators can display matrices and their inverses. To verify that two matrices are inverses, you just simply multiply. Okay? That's important for you to know. The inverse matrix theorem. If A times D minus B times C cannot equal 0, and M equals the matrix A, B, C, D, then the inverse matrix is equal to, okay? And what you're going to look here is, I want you to look at the numerators. What happens is your A and D just flip spots, okay? A and D just flip spots, okay? B and C just gets a negative symbol put on it. Okay, so it's opposite. Now, all these are divided by this. A times D, C times B. A times D minus B times C. So, in essence, we could rewrite this inverse matrix using a scalar multiplication, which you're going to see on the next page, but I'm going to show you right now, is 1 over AD minus BC times the matrix D, negative B, negative C, A. You just flip A and D, put negatives on the B and C, and then multiply it to this thing right here, A times D minus B times C. Okay? It says use the inverse matrix theorem to find the inverse of each matrix, if it exists. So, as I said before, the first thing you got to do is take A times D minus B times C. So we got to find that out. So a negative 2 times 6 minus a negative 1 times 4. Okay, negative 2 times 6 is a negative 12. A negative times a positive is going to be a positive. So 4 times 1 is 4. So I get out a negative 8. So this does exist. So my inverse, and I'm just going to call this M inverse, is equal to 1 over this thing, which is a negative 8, times the matrix. Flip-flop these two, so 6 goes here, negative 2 goes here. This positive 4 now becomes a negative 4. This negative 1 now becomes a positive 1. We can multiply this all the way through and have it look at that matrix. And so my answer would be 1/8 times this, or a negative 1/8 times this, which would give me a negative 6/8. Negative 4 times that gives me a positive 4/8. 1 times that is a negative 1/8. And a negative 2 times all that is a positive 2/8. Now we could reduce these down, call them a negative 3/4. We could call this 1/2. We could call this 1/4, and that would stay the same. Okay? Now, same thing up here. Crisscross these, okay? So 6 times 5 minus 10 times 3 gives me 30 minus 30. That equals 0. If that equals 0, you cannot find a matrix, because I can't put 1 over 0 and then multiply it to some matrix, because 1 divided by 0 is undefined. So it says, if a matrix has no inverse, trying to find it on a calculator leads to an error message. Some calculators say the inverse is undefined, while others say the original matrix is a singular matrix, meaning that its inverse does not exist. So let's put that one on our calculator just to show you what it would look like. So I hit second function matrix, and I'm going to edit A here. It's a 2 by 2. Goes 5, 10, 3, 6. Okay. I hit second function quit. And if I hit second function matrix, okay, I name it, that's my A, okay, and then put this negative 1 on it, that's going to give me my inverse matrix. I hit enter, and as you can see, it says error, singular matrix. So if this happens during a test or quiz, you can't say Mr. Johnson did not show you. When it has a singular matrix, there is no inverse, okay? No inverse. So moving along. Determinants and inverses. The formula in the inverse matrix theorem can be simplified using a scalar multiplication. This is what I showed you. 1 over all that times that matrix, okay? Because the number A times D minus B times C determines whether or not a matrix has an inverse, it is called a determinant. So a determinant determines if it has a matrix or not. We abbreviate the word determinant as DET. Thus, the inverse matrix theorem can be written: if M equals A, B, C, D, then the inverse matrix equals 1 over the determinant of M times the matrix D, negative B, negative C, A, if and only if the determinant of M does not equal 0. Calculators that handle matrices have a determinant function, usually called DET. Okay? Very important. So A says, use a calculator to find the determinant of this. Okay? So let's go to our calculator. I'm going to second function matrix. I want to go to edit, and I got to type in that matrix. So a -3, it's still a 2 by 2. So a -3, 5, 7, -11. Okay. I hit second function quit. Okay. If you go here, second function matrix, and you go to math, notice the DET, that's the determinant. The determinant's going to tell us if it has a inverse or not. So I hit that right there. I hit second function matrix name, which is number 1. I hit enter, and I get out a -2. Okay, so the determinant of this matrix, -3, 5, 7, -11, said that it equaled a -2. So let's check that. Doing it by hand. So by hand, it's just A determinant equals A times D minus B times C. This is A, this is B, C, D. So A is a -3 times B, or D, which is a -1, minus B, which is 5, times C, which is 7. So a -3 times a -11 is a positive 33. A -5 times 7 is a -35. And that equals a -2. So these both check out. That's all I have for you today. Please enjoy. We'll see you tomorrow.